Two ships are located in a north-south line. Ship B is to the south of ship A, 10 kilometers away. They start moving simultaneously at say 10 km per hour. Ship B moving eastward and ship A southwards. Our interest is to determine the minimum distance between the two during the subsequent motion. Straightforward way of doing this is find the distance between the two as a function of say time and let math take care of the remaining process. For that we'll visualize this. At some arbitrary moment of time t after they start moving, let the ship B be at C and ship A be at C and ship B be at D. Ship A has covered distance AC, that's Vt, and this BD, which is also Vt. These are equal here. The line joining the two ships, this line, the length of the line is varying. Initially that line's length is equal to 10 kilometers, that is, say, let's call that D. So this length L of this line, L, is this is Vt, and if you call this distance D, this is 10 kilometer, that L would be root of D minus Vt whole squared. This is D minus Vt and this Vt, so plus Vt whole squared. So got L as a function of time. We want to find its minimum. We can differentiate L and find the minimum, but I think we can as well differentiate square of L. Here L is positive and minimum of L squared would also be minimum of L. So let's call this capital L squared is capital. This will be D minus Vt whole squared plus Vt whole squared. So dl by dt would be 2 into d minus Vt into minus V plus, this is V squared T squared, so T squared will be 2T, so 2V squared T. We'll set this to 0. So 2 gets cancelled, so let's try that here. 2 into d minus Vt into minus V plus 2V squared T equals 0. 2 gets cancelled out, 1 V gets cancelled out, and you see d minus Vt, that's a minus sign here, plus Vt is equal to 0. So this will give us 2Vt equals d, or t equals d by 2V. That's it, we got the time when the distance is least, and that least distance can be got by substituting for a t here. That t is d by 2v, or Vt is d by 2, this Vt is d by 2. So this will be that L minimum L is root of d minus Vt. Vt is d by 2, so this is d by 2 whole squared plus d by 2 whole squared. So root of d by 2 whole squared plus d by 2 whole squared. So the root of d by 2 whole squared plus d by 2 whole squared, and this is equal to, well, d by root 2. So simple enough, we found when the distance will be minimum and what's the time when they'll be at minimum distance. This is 10 kilometer and this is 10 kilometer per hour, so this will be half an hour. So that's one way of solving. Minimum distance is d by root 2, this is 10 by root 2 kilometer. Another way of looking at the situation is this. This is the arbitrary moment of time when the ship A has moved some distance and ship B has moved some distance. Let the velocity v of this ship A make an angle theta with the line L joining the two ships. and let this angle made by the velocity of ship B with the line joining be phi. This is phi, right? Phi and phi. So L increases at the rate v cos phi due to B's motion, and it will decrease at the rate v cos theta due to A's motion. This is the rate of change of L. We're getting that directly. So ends of this line are moving at different speeds, and we're getting the components of the velocities along the line. V cos theta causes the length of the line to decrease, and v cos phi causes the length to increase. At the initial moment, theta is 0 and phi is 90. So theta is 0 and phi is 90. So dl by dt is minus v. That is, if say ship B were not moving and ship A alone were moving, the length would be decreasing at the rate v, right? So that's the initial moment. So what happens with time is that this theta is going to change. It's going to increase. And as theta increases, this decreases. So the rate of change, well, v cos phi and v cos theta change at different rates. So initially dl by dt is negative, length is decreasing. At some moment the angles will be such that these two are equal. That will be dl by dt will be 0. And then subsequently L will start increasing. So you can see that phi initially is 90 and goes on decreasing. Theta is initially 0 and goes on increasing. So the line length of the line varies at a varying rate. Initially the length decreases, becomes minimum, and then increases. So when length is minimum, this dl by dt would be 0. That's v cos phi minus v cos theta would be 0. That will be cos phi equals cos theta, that is phi equals theta. From this figure you can see phi plus theta is 90 degree. So when L is minimum, phi and theta are equal to 45 degree each. Phi equals theta equals 45 when L is minimum. So, and then how do you see when say when these angles are 45, let's call this say x, this will be d minus x. If this is x, this is also x, right? So these ships have moved equal distance. So this is d minus x and this is x, and so when the angles are equal, this d minus x will be equal to x, where x equals vt. So what do you get? X equals d by 2. So when the length L is least, this is d by 2 and this d by 2. So this is the root of d squared by 4 plus d squared by 4. So we got this earlier too, right? That's this is going to be, L minimum is going to be root of d by 2 whole square plus d by 2 whole square. That will be d by root 2. So that's it. We got what we want. We got the distance as d by 2. The distance which each has moved is d by 2. So d by 2, and we can get the time. Time when this happens will be d by 2 by v, d by 2v. So time also we got when the distance L is minimum, that is d by 2. Each ship has moved d by 2 and they moved it at v. So d by 2v, 10 kilometers, and v is 10 km per hour we said. So this will be half an hour. So there we are. We got minimum value for L in I think a little simpler manner. We look directly at L and how it changes. Yet another way of solving the problem is to switch to the reference frame of one of the ships. In the reference frame at rest with respect to water, the ship A and B are 10 km apart at the initial moment, and ship A moves southward and ship B moves eastward. Let's move to the reference frame of A. In this reference frame, the ship A is at rest, and ship B, well, we want to find the velocity of ship B relative to A, and this is got by adding the reversed velocity of A to B. I am saying it's addition of reversed velocity. I'll explain that in a separate video. So we are adding reversed velocity V A to B, and what is that now that's happened? A is imagined to be at rest and B is moving at this velocity. So reversed velocity of A, that's northward, you add these two. These are equal vectors, so this angle will be 45 degree, and root 2V is the value of this. So this is velocity of B, this is the reversed velocity of A, right? This is minus VA bar, this VB bar. Reversed velocity of A is being added, and we got this. Its magnitude is root 2V, the angle direction is 45 degree. So the line of motion of B would be like this. B seems to move northeast in the reference frame of the ship A. So A is at rest. So minimum distance is when you drop a perpendicular, that will give you the minimum distance. So the minimum distance is when, well, this is the line of motion, only B is moving here, right? A is at rest, so minimum distance is this. And this is D, this angle is 90, right? This is 45, right? This is 45, this is 45. This is northeast, this is 45, so this must be 45. So minimum distance, this is, say, this is D cos 45. Minimum distance is D cos 45. This is D, and that's 45 degree. That will be D by root 2. So one simple answer here. This is minimum distance. And when does this happen? The time when this happens? This is the distance moved by the ship B, right? That will be D by root 2. And it is moving at root 2B. D by root 2 at root 2B. This is the time. This is D by 2V. 10 kilometers, 10 kilometers per hour, so 10 by 20, that's half an hour. We got this result earlier too. So we got the minimum distance and we got the time using the reference frame of the, well, ship A. What you should understand here is that in this reference frame A hasn't moved, B alone has moved, right? In the reference frame, the observer attached to the water, say both ships are moving. So distance moved by the ships will be different for different observers. Time that we got and the minimum distance we got are the same in both the reference frames. You will learn later on that time is also relativistic, that is different observers find the interval between events to be different, well, if they are moving. So different moving observers will find the time interval between two events to be different. That's when the speeds are very large, at relativistic speeds. In classical mechanics, the mechanics we deal with at our level, we just can forget that time is not relativistic. So very elegant answer. So well, and you can see we haven't done much of math here. Well, this is a decent physics that we have here. An observer who imagines himself to be at rest by assuming that the object he is observing has its reversed velocity in addition to its own velocity. Its own velocity was VB, reversed velocity because of A's motion. A is assuming he is at rest, so this is what is happening here. Good to do it this way too.